Hello everyone. Now in today's tutorial we'll be learning how to solve this nice thermal physics problem. Okay, this is one of the questions sent to my mail. Okay, I got this question like 2 days ago. Okay, so now let's see how this question can be demystified. Okay, we have a plastic kettle with 0.6 kilogram of water at a temperature of 20 degrees Celsius. Okay, a 2.2 kilowatt electric heater is used to heat the water from it for a time of 4.0 minutes. 4.0 minutes. So the specific heat capacity of water is 4200 joules per kilogram per Kelvin. Okay, okay, for a time of 4 minutes. Okay, and the specific latent heat of vaporization of water is 2.3 times 10 raised to the power of 6 joules per kilogram. Okay. Now the boiling point of water is 100 degrees Celsius. So we want to calculate the mass of water remaining in the kettle after 4.0 minutes. Okay, after 4.0 minutes, assume that all the thermal energy from the heater is supplied to the water. Okay, is supplied to the water. Okay, now this is how we're going to solve this question. Okay, I think we'll need to, okay, we have a kettle. Okay, we have a kettle. That's okay. Okay, so this is the kettle. So water is kept inside the kettle. Okay, so this is water. So mass of water is 0.6 kilogram. Okay, so what again? Now the temperature. The temperature, that's the initial temperature, is 20 degrees Celsius. Okay, so we have that a 2.2 kilowatt electric heater is used to heat the water. So let's say we have a 2.2 kilowatt electric heater. So now let me draw that. Let me draw it this way. Electric heater. This is the terminals. Okay. So we then have this, this. I have to draw it this way. Yeah. We have different types of electric heater. So this is now connected to the source of electricity. Let's say this is the source of electricity. It is connected to the source of electricity. So this is a connecting wire. So what this means is that, so this is just like the what's it called? The kettle is open when the kettle is left open. So we have the electric heater. Okay, so the rating of the electric heater is 2.2 kilowatts. So that means then the electric heater is used to heat the water for a time of 4.0 minutes. So remember, we have now, these are the values we are giving. Now we have given values. Given values, we have mass of water. Okay, mass of water is 0. We have 0.60 kilogram. Okay, now then we have temperature. Temperature of water, that 20 degree Celsius. Okay, now then the heater. Okay, now we're giving the power, that's that's heater rating. Okay, that's electric heater rating, that's the power rating, is given to be 2.2 kilowatts. Okay, then time, the time during which, the time during which current is passed is 4 minutes. So time during which current is passed through the heater, okay, is 4.0 minutes. So that's 4.0 minutes. So we're also given the specific heat capacity of water, which is 4200, okay, kilojoules, no, joules per kilogram per Kelvin. Then the latent heat of vaporization of water, yeah, latent heat of vaporization of water is given to be 2.3 times 10 raised to the power of 6 joules per kilogram. Now, why it is important for me to write this is because it will help me to, in order to know, as in to navigate through the solution. So what we have here is, now the first thing we need to do, okay, the first thing we need to do in this case is to calculate the energy supplied by the electric heater. Okay, so step one, calculate the energy, okay, supplied by the electric heater. So the energy will be the product of power and time. So we have here that the heater rating, which is the power, is what? 2.2 kilowatts. Okay, so which means P equals to 2.2 times 10 raised to the power of 3 joules per second. Okay, that's the power. Now the time is 4.0 minutes, and that will be T equals to 4 times 60 seconds, and that will be 240 seconds. So the energy supplied will now be E equals to, we have PT. So E will be equals to, now 2.2 times 10 raised to the power of 3, that will be 2200. So that will be 2200 multiplied by 240. So here we have joules per seconds, the units, multiplied by seconds. So the unit of energy will become joules. So we have 2200 multiplied by 240. That will be 528,000. Okay, so we have 52800 joules. So this is the energy supplied, okay, by the electric heater. Yeah, that's the energy supplied by the electric heater. So we have the specific heat capacity of water is 4,200 joules per kilogram per Kelvin. And the specific latent heat of vaporization, which is the energy required, to convert 1 unit mass of water, okay, into vapor without a change in temperature. All right, so that's latent heat of vaporization. And the heat, okay, will be absorbed from the surrounding while the temperature of the substance will remain constant. That's in the case of latent heat of vaporization. So now step 2. Okay, so because the water temperature, the first temperature of water is 20 degrees Celsius. That will be the initial temperature. So now let's calculate the heat, okay, the heat required to heat water from 20 degrees Celsius to 100 degrees Celsius. Okay, yeah. So step 2, okay, calculate the heat energy. Okay, the heat energy required to heat water, okay, from 20 degrees Celsius to 100 degrees Celsius. Yeah. So in this case, we are going to use the heat will be Q equals to mass of water, then specific heat capacity of water multiplied by temperature difference. So the temperature difference will be 100 minus 20. Yeah. So in this case, we are going to have mass of water is 0.60 multiplied by 4,200, then multiplied by 100 minus 20. So this will be 0.60 times 4,200 multiplied by 80. Okay, so so we have 0.60 multiplied by 4,200 multiplied by 80. That will be 201,600. So we have 201,600. So in joules. So this is the heat This is the heat required, to heat water from 20 degrees Celsius to 100 degrees Celsius. Okay, so now, so we have here that we want to calculate the mass of water remaining in the kettle. Now, after 4.0 minutes. So that means we need to calculate the heat energy remaining after water is heated from 20 degrees Celsius to 100 degrees Celsius. Yeah. So then step 3, okay? Step 3 is to what? To calculate the heat energy remaining. Yeah. So the heat energy remaining after water is heated from 20 degrees Celsius to 100 degrees Celsius. So that means that will be the difference. So the energy remaining, so this is the energy remaining, that will be equals to this energy, okay, minus Q. Yeah, that will be that energy minus Q. So we have the energy remaining to be equals to this value. Okay, so we have 528 52800 minus 201,600. Okay, so let's get the heat energy remaining. 528,000 minus 201,600. Okay, that will be 326,400. So the energy remaining, okay, the energy remaining will be 326,400. 326,400 joules. 326,400 joules. That's the energy remaining. So now what I've done here is, now the question is not difficult to to understand, but what is important is, okay, anyway, let me say I'm just seeing this for the first time, so that's why I'm taking my time to navigate through the solution, like I said. All right, so now we have a plastic kettle with 0.60 kilogram of water at a temperature of 20 degrees Celsius. So which means the initial temperature of water is 20 degrees Celsius, okay, and the mass of water is 0.60 kilogram. Okay, so we have we have the electric heater rating to be 2.2 kilowatts, okay, and is used to heat water for a time of 4 minutes. So that means the electric heater will supply heat to water. That means when current flows through the connecting wire, now the current will flow through the wall, the heating element, and the water will then absorb it. When they absorb it, the temperature will rise, from 20 degrees Celsius to the boiling temperature of water, which is 100 degrees Celsius. So we know that water boil at 100 degrees Celsius. So now if heat is continually supplied to water when its temperature is already at 100 degrees Celsius, the temperature will remain the same. Okay, it will not increase, it will remain the same. And that's why we have latent heat of vaporization. Yeah, that's why we have latent heat of vaporization. So because we want to calculate the mass of water remaining in the kettle after 4.0 minutes, okay, and we are to assume that all the thermal energy from the heater is transferred to water. Okay, so we just calculated the heat energy supplied by the electric heater to water, okay, and then the heat energy required to heat water from 20 degrees Celsius to 100 degrees Celsius. Okay, then we have here that, okay, so then we just calculated the energy remaining. So this is the energy remaining. So the next step, which is step 4. So step 4 will now be, now that we know the energy remaining, so mass of water, and we are giving latent heat of vaporization of water. Latent heat of vaporization is the heat energy required to break the bond between liquid molecule by allowing them to go into vapor phase, okay, at a steady temperature. Or we can say the heat energy required to convert 1 kilogram mass of water into vapor without any change, okay, any change in temperature, because like I said, the heat will be absorbed from the surrounding, but the temperature of the water will remain constant, or the temperature of the substance will remain constant. All right, so for step 4, so now what to do now is to calculate the mass of, want to calculate the mass of water remaining. Okay, now the mass of water that can vaporize, okay, that can be what? That can be vaporized. Okay, so this time we calculate the mass of water, okay, that can be vaporized, or we can say that vaporize. Let's put it that way, that vaporize. Okay, the mass of water that vaporize. Okay, the mass of water that vaporize. So which means we're going to make use of Q equals to, that is the energy remaining. Okay, energy remaining. I'm used to that. Okay, energy remaining equals to mass of water multiplied by latent heat of vaporization. Remember, now when the water is heated, when water is heated, the fast energetic particles or molecules of water will escape into the top space above water. And when they accumulate the top space above water, they will accumulate the top space in the form of vapor. So that is the mass of water that vaporize, or that can vaporize. So that's what we have as that step 4. So this mass of water that vaporize, okay, that vaporize will now be equals to the energy remaining, okay, divided by latent heat of vaporization. So mass of water which vaporize. So the energy remaining, we found that to be this value. Okay, so we put 326,400 divided by, now the latent heat of vaporization, yes, 2.3. We have 2.3 times 10 raised to the power of 6. Okay, so let's divide this. Now we know that 326,400, okay, divided by, when we multiply that, that'll be 2300,000. That 10 raised to the power of 6. That's okay. So that'll be 0000. Okay, so that'll be 0.1419. Okay, so we have mass of water that vaporized to be 0.1419 kilogram. Okay, so that's the mass of water. Okay, mass of water that vaporize. Okay, so now to calculate the mass of water remaining in the kettle after 4.0 minutes. Okay, so that would mean that we are going to subtract, okay, we're going to what? Mass of water remaining, mass of water remaining will be equals to mass of water minus mass of water that vaporize. Okay, so that will be equals to 0.60 kilogram minus 0.1419 kilogram. Okay, so 0.60 minus 0.1419, that will be 0.4581. that will be equals to 0.4581 kilogram. So mass of water remaining is equals to 0.4581 kilogram, and that is the mass of water remaining in the kettle, okay, after 4.0 minutes. Assume that the thermal energy from the heater is transferred to the water. The noblest pleasure is the joy of understanding. Bye-bye.